Hello, it's Keith here, and this is the first in a new series of assembly programming tutorials, this time on the 6809, because I didn't think I was covering enough processors already, it seems. So what's the 6809? Well, the 6809 is a bit like the 6502. It was based on the 6800, but it took a different path. Now, the 6809 was trying to, I believe, emulate the PDP-11. It was trying to mimic that. I've actually read that was one of the intentions of its creation. I don't know that I would have said that, but I would say that it's certainly very powerful compared to the 6502. I find it a very, very flexible processor. It's very interesting, although it is quite different, and being different kind of makes it difficult if you're familiar with 6502. We're going to go over the basics today, and this is going to be a long-running series. Like all my other series, we're going to cover all of the content that you're going to need for basic programming of this system. Now, why would you be interested in the 6809? Well, if you're a Dragon fan, the Dragon 32, Dragon 64, then that would be a good reason. If you're a fan of the FM7, a Japanese system, which you might not be familiar with in the West, I understand that, but I was interested in it, and that is a very popular 6809 based system. But for me, the real clinching factor for why I wanted to learn this processor was the Vectrex, because the Vectrex is pretty unique in the classic computers world, in that it had a vector-based CRT display that really was very different to everything else on the market. And so I wanted to cover this system, and because I've now done these tutorials and learned 6809 to a basic level, I can now write some Vectrex programs, and we're going to, of course, look at that later on. But obviously, we're going to have to look at the basics of the processor and learn how it works. Now, if you're familiar with the 6502, you're going to have a good starting point because the 6809 has a lot of similarities. If you're familiar with the Z80 or the 68000, you're going to at least know hexadecimal and things like that. So you're going to be familiar with the basics either way, but the 6809 really has some unique things that are going to be a bit of a surprise. So we're going to go through all of those things, and we're going to learn the essentials of the 6809 processor. Okay, so I'm going to go over pretty much everything you're going to need, but I am going to assume you've got some kind of understanding of things like hexadecimal and binary. I'm assuming this isn't your absolute first time using those things, but if you've never done any assembly before, I'm intending this is still going to be fine for you. I'm not going to assume you've done any of those other processes, although obviously it will help you if you have. Now, let's have a look at the 6809 registers, and you're going to see pretty quickly that while it looks a little bit like the 6502, it's only a little bit like the 6502. We've got the classic A register, which is an 8-bit register. We've got X and Y registers, although they are now 16-bit registers. We've got a stack pointer, which is also 16-bit. We've got a second stack pointer known as the user stack. I know we're kind of into crazy territory there, but we've got two. The 0 page is now called the direct page, and it can move because it no longer has to be at 0, although we will always have it at 0 in these tutorials, but it can move. That's something that Vectrex takes serious advantage of. We've got a flags register called the CCR, but we also have a way of using the two 8-bit accumulators, A and B, together as a pair for something known as the double accumulator, which is D. Now, when the two registers are combined, A takes the top half and B takes the bottom half of the register. So A is the high part and B is the low part of that pair. So we're going to have all of these, and of course if we're using D, then it is actually changing the values of A and B. They are the same register. D isn't separate to A and B in any way. Now if you look at these, you'll see that really in my mind the 6809 is a bit more like the Z80 in that it's sort of partially 16-bit, whereas the 6502, all of the commands were really working at the 8-bit level. The 6809 has some 16-bit registers, and it can do some more 16-bit-like things. And of course, that adds some extra complexity. What it also has is a ton of addressing modes, and we're going to go over those later on in a following lesson. Another important thing to point out is that, like the 68000, the 6809 is one of the rare processors that is big endian. And again, if you're familiar with 6502, that's probably going to be something that might catch you out. But as I say, generally speaking, it's not going to be too shocking to you if you're familiar with the 6502 seeing this processor, because there's more that's the same than there's different, and I think you won't have too much trouble, getting to hang of it. So you can see we've got lots of addressing modes here. We're going to cover those next time though. our first lesson is going to be the same as all my other tutorials. It's just a getting started. We're going to go over the basics of the scripts I'm using, and we're going to look at the really simple commands for setting registers and things like that. The stuff that you're going to need as a fundamental. So let's go over to our source code and let's see what we'll be doing today. Okay, so here is the first program I'm going to show you. This is my minimal example, and if you are looking to completely ignore my tutorials, which, great if you can, feel free. This is my minimal example, which will just compile a running program on all of the systems we're going to be looking at in these tutorials. Now, the tutorials, as I say, are going to cover 3 systems. They're going to cover the Dragon and the Tandy Coco. They're basically the same machine, I believe. So you can see here, we've got a Hello World example here. Now this code is showing the contents of the registers to the screen. If I just lock this to the top here. So this is showing the registers to the screen, and you can see 1, 2, 3, 4 in the D register, which is A and B combined. And you can see all the other registers as well. And then we've dumped some memory from C000 here. And then we've shown a Hello World message to the screen just as a test. Now, unfortunately, the Dragon doesn't have any lowercase, so it's all in uppercase, but my functions that do print string and print character, they are coping with that for us. So if you were looking to write your own program, you would want to replace the part in here. Now the header and the footer are of course doing all of the things with regards to setting up the system, making sure we've got a valid file and setting up the screen as required. So you can see here this example was running on the Dragon there. We can also run it on the FM7 here, which is the Japanese machine, which I'm living in Japan and I didn't grow up in Japan, so I find these machines I've never heard of very fascinating. So here is the FM7. You can see it's the same example running pretty much in the same way. And then finally, we can also run this just about on the Vectrex. So here you go. Now you can see there's a slight flicker here, and that's because the Vectrex, if you draw too much onto the screen, it starts slowing down. It can't draw everything before the persistence of vision starts to fade on the phosphors. So it's not going to be perfect, and some of the stuff won't work so well on the Vectrex, but at least the basic example you can use as is. And so first of all, let's just quickly go over the very basic contents of this. Now we've got an include here, and this is a file. So this is including a file that's doing some work here. We've got some commands here. We've got a jump here, and this jumps to a label. Now labels, this label in particular is included in one of these files, but you can see this infinite loop is also a label. Labels are always at the far left, and I always put a colon at the end of them. The commands are always indented by a tab, and you can see there's comments with a semicolon here. So this is the sort of basics, and as I say, if you were wanting to start from scratch, you'd probably want to just replace this bit here with your own code. Okay, now one other thing to just point out is the Vectrex. You do have to redraw the screen every frame, so there's a special bit of code here just for the Vectrex, and I've got this if-def which says if build VTX is defined. That's a symbol. We're going to look at that later. So if that's defined, we're building for the Vectrex, and when I compile, if I just press F6 here, I've got a list of options here, and these batch files are defining when we're building for the Vectrex this build VTX here. So that's just for that version. So that's my minimal file, but what we're going to look at today is this lesson 1 file here, and we're going to be testing this out, and it's got a variety of commands that I think are going to give us a brief introduction to the simple commands for setting registers and reading memory and things like that, the real basics of the language that are enough to give us a taste of it and hopefully get you interested for later lessons. Okay, now one thing I do want to point out first though, just before, is as I say, this will compile onto Vectrex, FM7 and Dragon. Now I'm going to be using the FM7 because the displays I think is the most comfortable and it's slightly bigger. I did actually write all of these for the Dragon though, so they should work pretty much the same for the Dragon. However, they won't necessarily work for the Vectrex. Unfortunately, because of the layout of the memory and things, and in some cases like the Vectrex, the operating system calls that do the drawing, they use parts of the 0 page. It's very difficult to get these to work exactly the same on all systems. So I would recommend, if you can get it working, the FM7. The Dragon should be okay as well. The Vectrex, these examples won't really work on that system. Now, because of legal reasons, I can't provide ROMs with the emulators, so you're going to have to find your own Dragon or FM7 ROMs to run this. So you'll need to put those in the same folder as the emulator. I'm afraid that's just, I can't do it. So please bear with me with that, I'm afraid. So anyway, we're going to be testing this on the FM7. Okay, so let's just fire up today's example on the FM7 here. Okay, so here's the example. Now, hopefully you can see the screen here. Unfortunately, the interlacing of the FM7 is a little bit tricky, so hopefully that's going to be visible okay, but I'll read out all of the content anyway, just in case it's not. Okay, so the first example we're doing here is just some very simple mathematical examples here. Now, you can see we've got a whole list of commands here, and each one starts with LD, and then there's a letter. Now, LD stands for load, and the letter is the register that we want to load into. So LDD means load into the D, double accumulator. LDX means load into X. LDY means load into Y, and so on here. So first we are loading the double accumulator with a 16-bit value 1234 in hexadecimal here. Now, all of these examples here you can see are going to be shown to the screen by this monitor command here. JSR stands for jump to subroutine, and monitor is one of the tools in the functions that I've provided. So we're not going to look at the contents of that because it's quite complicated. So we're loading 1234 in as a 16-bit value here, and you can see it's been loaded in here. As I said before, the top half of D is A and the bottom half is B. So those are the two 8-bit accumulators, but they make up this 16-bit dual accumulator here. Now, after that, we're loading X with 5678. X is always 16-bit, and X has the same function as X did on the 6502. It's just been expanded to 16 bits now. Now, when we loaded 5678 here, this is a decimal number, and it's been converted to 162E in hexadecimal. And the reason it's decimal is we didn't specify the dollar symbol here. Now, when we specify the dollar symbol, that specifies a number as hexadecimal. When we don't, it specifies it as decimal. The hash symbol specifies an immediate value. So this is saying load the immediate value 1234 into D. And we'll see what happens in a moment when we don't include that hash symbol. Here, we've got a percent, and that specifies a binary number. And so here we've loaded 12 bits of binary into Y here. And so you can see Y has loaded in 0AF0 here, which is the value made up of these binary bits here, and that's done by that percentage symbol. Now, next we're going to load the stack. There are, of course, two stacks. There's the regular stack, which is very important. We'll go over the stack in a later lesson, but the stack is used by things like the subroutines, so we need to make sure it's a valid stack, and for that reason I'm using a different address on the FM7 and the Dragon, because otherwise I might crash the machine. And so we're loading a stack pointer for S here, and you can see that the stack has been loaded in here. Now it's actually changed very slightly, and that's because of the subroutines being called. And then finally we're loading the user stack, and we're loading in DEFO here into that stack U here. You can see that just there. Now the user stack isn't used in any way by the system. It's not like the processor doesn't ever use it, so we can do whatever we want with it, but it does function in the same way as the regular stack, in the sense that we can push and pop values to it. Again, we'll cover this later on, so don't worry if you don't know what that means, but it's basically totally for our use. The S stack is the system stack, the U stack is our own for whatever we want to do with it. Now, in this example, I've been using the D accumulator, the double accumulator, and I've loaded 1234, but we can load that in two separate parts here. In this example, I've loaded an A, which is hexadecimal 41, and then I've loaded the B accumulator with 22 in hexadecimal, and you can see that's loaded in just here. And as I said before, A is the top half and B is the bottom half here of the 16-bit double accumulator there. Okay, so that's how we can load values. This time we're going to look at storing values. Now, when we want to store a value, we use ST for store and the letter of the register we want to store. So STD will store the double accumulator, STX will store the X register, and so on. Now, before we had all of these hash symbols to specify an immediate value, but if we take away the hash symbol, it means we're specifying an address, which is what we're going to want to do when we're storing a value. So STD hexadecimal $symbol 6000 means store the double accumulator to memory address 6000 and 6001, and remember this processor is big endian, so the top half, the A part, will be stored to 6000 and the low part, the B part, will be stored to 6001. That's a typo there, that should be B. There we go, 6001. Okay, and we can confirm that in just a moment. So here we were storing the double accumulator, which now had the value 4122, and we stored it to 6000, which is this address here, you can see 41, and 6001, you can see that here, 22. Okay, so we were able to store the value to the 2 consecutive bytes of memory, and as I say, it's big endian, so the A part, the high part, came first. Now we've done that as well with all of these other examples, storing X to 6002 and of course 6003 because X is 16-bit now. And so you can see that X was 162E and those two values have been stored here as expected. And we've done the same with all of the other registers, and you can see we've got options for all of these 16-bit pairs here. We can also store the accumulator as two separate parts here though. So here we've stored A to 6009 here, and you can see that just here. And here we've stored B to 6000 and A here, and A is of course 1 after that. So you can see that just here. So you can see here that we've got all of these store commands, and we can specify memory addresses by simply not putting that hash symbol. And if you're not familiar with 6809, that's going to be a common mistake you're going to make. You're going to want to load in a value of 1000 in hexadecimal, but you'll forget your hash and you'll actually load in from memory address 1000 rather than the value 1000. It's a very common mistake, and it's one you do have to get used to. And you can see here, in this case, we've got more load commands. And in this case, we are specifying in some cases the hash and in some cases not. And just depending on whether that hash is there or not there, it's going to depend on whether we're loading in a value or from an address. Okay, so let's continue to have a look at these options here. Now you can see here, in this case, we've loaded X from hexadecimal 6000, and we've specified hexadecimal with this dollar here. Now the second time we've loaded Y from address 24576, and we've not specified the dollar, so this time we're loading from a decimal address. Now 24576 is actually 6000 in hexadecimal, and you can see the effect of this here because X is now 4122, and you can see that's been loaded in from this address here, 6000, and Y is also 4122 because again we loaded in from the same address. So these are both effectively the same value, it's just the dollar specifies hexadecimal and the lack of a dollar specifies decimal, and of course the lack of a hash specifies that these were both addresses. Now these have all been addresses specified, and these are all 16 bits. Now what happens if we only specify an 8-bit address? Well, the 6502 people will know exactly what happens. It loads in from something that's typically known as the 0 page, and this is where the top byte is 0 and the bottom byte is the byte specified. So this would be 0060 and this would be 0062. And so what we've done here is we've loaded the D double accumulator with 1234 and stored to 60, and then we've loaded FECD and we've stored that double accumulator to 62. And you can see that just here, this is memory address 0060, and we've written 1234 FEDC here. Now the important thing to remember, of course, with the 6809 is that while the starting position and the position we'll be using is that the direct page is at 0, so effectively exactly the same as the 0 page, if we change that direct page register to 02, for example, then these writes would not occur to 0060 and 0062. They would occur to 0260 and 0262, even though we only specified a single byte of the address. Now, that's in theory. As I say, we're not going to do that because it makes things overcomplicated, and in some cases it may cause problems for the operating system, but that's something that does happen with the Vectrex. The Vectrex does use an alternate direct page for its functions, so that's just something to bear in mind, that it's definitely an option, and it's wrong to assume that writes will always go to 00 for the direct page on the 6809 because it's not a limitation of the system. Okay, so now we've loaded and stored various registers. We've had a brief discussion of the direct page, although we'll cover it more next time when we look at addressing modes, and we've looked at the way that we can use hexadecimal, decimal and other formats. We're now going to have a quick look at a few alternate ways of setting registers. Now, in this case, we've been loading registers from immediate values. However, we can also swap and shift values of registers between registers. So in this case, for example, we might want to copy the D register to the X register, and we can do that with the TFR transfer command. We might also want to swap two values so that both registers have the value of each other, but that no value is overwritten, so they exchange rather than being copied. And we can do that with EXG, exchange. So in this case, we've transferred D to X. Now D had the value FEDC, and you can see here that D had FEDC and X had 0060. And after the command, both D and X were equal to FEDC. Now, in the second example, we've exchanged the Y and X registers. Now, the Y register had the value 0 and the X register had FEDC. And now the X register has the value 0 and the Y register has FEDC. But of course no other value registers are used as an intermediary, no other registers changed in this, it's just those two have swapped over, which is very handy really. Okay, so that's our second set of examples there. Let's move on and let's have a look at some more of the commands we have available to us. Now, like with most of the processors, we do have some commands for very simple mathematics that just take a single command. Now, there will be cases quite often with loops and things. We want to increment or decrement a register, basically add 1 or subtract 1. And we can do that with inc A or inc B or dec A or dec B. Now, note there's no dec D command. This is only done at the byte level, not the word level, because it is an 8-bit processor, I guess. So we've got those commands to do addition and subtraction from an 8-bit register here. We've also got some commands to set registers to 0. If we want to 0 a register, we can do a clear A or a clear B. But notice we don't have a clear D or a clear X command. These are just limited to the 8-bit registers, but very handy if we want to quickly 0 a byte here. Okay, so let's see these in action here. So here we've got our inc A, and you can see that the A, the high part here, it's gone up from 88 to 89 here. And we've done our dec of B, and B has gone from 88 down to 87. Of course, we could have done the opposite there with A and B. And then we've used clear A, and you can see the A part has become 0 here. And we've done clear B, and you can see the B part has become 0 just here. Now, although we can't do those on X and Y registers, we can do them on 8-bit addresses. So here we've done an inc on memory address 6000, a dec on memory address 6001, and a clear on memory address 6002. And you can see the results just here. Now, initially, these bytes were all 0. We inked this 0 and it went up to 01. We decremented this 0, and because of the way that hexadecimal works, it rolled back round to 255, which is FF. And we cleared the third one, but it was already 0, so we can't really see any result there, unfortunately. But yes, we have cleared 6002, and it's become a 0 there. Again, all at the byte level. These are byte commands. Okay, so that's a few handy commands for quick mathematical operations we will commonly need to do, and also setting zeros, which again, something we're going to need quite a lot, quite probably. Now, as well as being able to do additions and subtractions of 1, of course we can do additions and subtractions of much larger numbers if we wish. So here you can see we're doing add A, add B, and sub B here, and these are of course again working at the 8-bit level. And you can see here we've started with 8888 here in the double accumulator, which is the combination of A and B. We've added 4 to the A, and that's become 8C, and we've done the same to B, so that's also become a 8C. And then we've subtracted 4, and it's gone back down to 88 here. So you can see here we've been able to do these mathematical operations on the 8-bit part of D. However, we can also do these addition and subtraction commands in 16 bits. So here we've done an add D, and we've added hexadecimal 1, 2, 3, 4 to the double accumulator, and so it's gone from 8888 to 9ABC here. And we've subtracted that, and it's gone right back to 8888 here. Now, there is a special case where we can add an 8-bit register to a 16-bit register, and this is the ABX command. And what this does is it adds 8-bit register B to 16-bit register X here. You can see here in this case we've had X as 1, 2, 3, 4. We've loaded B with 4, and it's become 1, 2, 3, 8 here. Now, this is a very exclusive command. There's only the ABX. There's no AAX to add A to X, and there's no ABY to add B to Y. So it's really just a one-off special command here. But you know, quite a nice command to have. And say this is just a single byte command here, so it's very small and fast if you're trying to optimize your code. So if that's something you needed to do, that would be very handy for you to try and take advantage of. Okay, so that's quite a lot of mathematical commands to get started with, but there's just one final thing I want to cover in today's lesson, and that's just the basics of subroutines. I mean, we've been seeing subroutines here, and we've just completely skipped over them. These monitor commands here are indeed subroutines, and I do just want to finally discuss what subroutines and jumps actually do. Now, a subroutine is basically your go sub in BASIC. This is where you go to a subprogram, run some code, and then come back again. And when you come back, you carry on from where you returned. Now, the alternative is a jump, and this is basically like your go-to. You jump to a label, and you don't come back by default and run the code that followed the jump. Now, of course, you could jump back to a second label immediately after the first jump, but by default, you don't. So here we've got a jump to subroutine to this print character routine. We're not going to cover what that does here. What we are going to look at is this test subroutine here. So JSR stands for jump to subroutine, and we've jumped to the label test JSR here. And you can see that just here. Now we've got a return command, RTS, return from subroutine here. And when that occurs, the code will continue to execute immediately afterwards. Now, as well as our jump to subroutine here, we've also got a regular jump here, and we've jumped to skip. Now this is going to move program control from here to here, and these commands are never going to get run. Okay, so that's the theory. Let's fire this up and let's see what happened. Okay, well, we've got A, B, C, D, E on the screen here, which is not very imaginative, but we'll see why. So here we've loaded the accumulator with the letter A here, an immediate value, and we've run this print char subroutine, which prints a character, and then we've loaded a B, and you can see that as well. And then we've got to this jump to skip. Now, we were going to print an X here in theory, but we've actually jumped over that, and we've got to this, and so we've printed a C here. So our letter sequence is uninterrupted here, and then we've jumped to a subroutine here, which is going to print this D, and then the return occurs, and then finally we get back to here and we show the E, and then finally we've got an infinite loop just here. So you can see here that the jumps allow us to skip over bits of code, and the jumps to subroutine allow us to run a subprogram and then come back and carry on. Now, it might not seem what the use of a bit of code like this is in this case that we're completely skipping over. And the thing is, we're going to look at conditional jumps and conditional branches later on, and it will look a lot more sensible then. This was just a very simple example to discuss the jump command, the jump to subroutine command, and the concept of labels. And as I said before, labels rose at the far left, and I always put a colon on the end. It does depend on the assembler a little bit, whether the colon's required and things, but that's the best way of doing things to be reliable. Now, in this case, this example will of course work even on the humble Vectrex, which does have some trouble with some of the other examples, but as I say, I am trying to make these multi-platform tutorials, and I do quite enjoy making my code run on a variety of systems in the same way. So you can see here this example will work just fine on all of them. So there we go. So I thought that was a nice way to end this lesson on the 6809 with a bit of multi-platform code. So there we go. So we've discussed quite a lot today. We've gone over the basics of an assembly file. We've looked at the setting of registers, transferring registers to memory, simple additional subtraction. We've briefly discussed the direct page, and even briefly discussed subroutines and things like that. Now, I know we've gone over an awful lot today, and we've done it pretty quickly. So don't worry if you're a little bit confused, because this isn't the only lesson. There's going to be a series of lessons on this processor, and things will become a lot clearer as we go along. I like to try and give a good amount of information in the first lesson, but I don't expect you to fully understand all the things we've seen today, because we're still going to cover them in a lot more detail. Now, you can go onto my website, you can download the source code for today's examples. You can see on the screen here there is also a text-based equivalent of today's lesson if you want to just see it again a bit more slowly, and you can download the development tools, the build scripts, and the pre-configured assemblers, although you do have to find your own ROMs, I'm afraid. I've got no choice on that, but so you can hopefully get started and compile this program yourself with those pre-configured scripts so that you can get things working. And the idea is you try out the code yourself, make some changes and see what happens. That's the best way to learn these things. You can't really learn this kind of programming language just by seeing someone else run it, although obviously that will help. Anyway, I hope you've enjoyed this lesson. I hope you're going to come back for more. If you have enjoyed it, please like and subscribe. Liking the videos does help with the Google algorithm. Recommend them to other people. And if you've enjoyed it and you want to, please tell other people about it. Share it on social networks and things, because it helps people find my channel, and maybe they'll find something they like. Now, if you've decided 6809 is a bit daunting for you and you're not really very interested in the Vectrex and the Dragon and the FM7, I've got a lot of other tutorials on my site. Z80, 6502, 68000, 8086, you name it, I'm trying to do it. So please take a look around and see if there's something else you would prefer instead. But whatever you do, I hope you enjoy your programming projects and whatever other creative things you're working on. Thanks for watching today, and goodbye.